Whenever the country does something exceptional, the world sits up and takes notice. We feel a sense of pride. My references to Chandrayaan, the world can't stop gushing about what it has achieved, how it has achieved, and they still can't get over the fact
Whenever
that
the country does something exceptional,
achieve something as
the world
fantastic
sits
as that
up
at
and
such
takes
low
notice.
cost.
To tell us
We feel
all
a sense
about
of
it,
pride.
we have
My
somebody who
references needs no introduction.
Chandrayaan,
He's the right
world
person.
can't
He's the
be-
chairman of ISRO.
can't stop gushing about
Somanath, what it has achieved.
Thank you so much for
How it has achieved.
having us here,
And they still can't get over the
agreeing
fact
whenever
that
the
to
country
us
does something
and
exceptional.
congratulations
something as
the world
fantastic
wants
as
it
that
fantastic
at
such
such
low
low
cost.
cost. We have gotten used
tell
to
us
getting
all
a sense
about
of
it.
pride. Surprises
We have
from
somebody who
and I'm referring to the
no introduction.
of that
He's the right
world
person.
can't
He's the chairman of
Vikram
ISRO.
can't stop
Against
gushing
the
about,
world,
which was
what
not
it has
expected.
achieved.
Thank you so much for
How
having
it
me
has
on the
achieved.
22nd,
And they still can't
when
get over the
we-
fact
whenever
that
the
to
sunlight
us
starts
and
beaming on
congratulations
something
as
as the moon where Pragyan and Vikram are, what do we expect?
With all our confidence on what we did for Chandrayaan 3, the Vikram lander and the rover, and also of the confidence that we have based on the test programs, we are hoping that both of them will come on. And it's important that both should come on. Coming on means that the electronics in the system should be functioning such a way that we should be in a position to send commands to it so that they will obey us when we want them to do something. And if it happens on 22nd, it's going to be history, because surviving such a very low temperature for long duration and making sure the systems work again is really going to be a tough thing.
Was it tested here?
See, what we did is we tested it in temperatures of similar nature. Of course, especially the rover, the Pragyan has been fully tested. But when it comes to Vikram, I can't say that everything is tested. It is such a huge item which can subject to such a low temperature testing. But many of the design heritage of the systems inside the Vikram lander and Pragyan being the same, we are hoping that whatever test we did on Pragyan should be sufficient enough to say, give confidence to the Vikram as well. But everything need not work in Vikram. At least if it's the communication system work and the primary computers work, we should be able to command it and then make the Pragyan raw once again.
So the command goes to now Pragyan or to Vikram?
It actually received in Vikram, then it need to be sent to Pragyan for it to do the. So the communication is established between the antenna on the Pragyan to Vikram. So this communication channel should be open for either to send a command or receive a data, like the cameras. You can see the cameras, two small cameras in front. So these are the cameras. So these cameras should take pictures. And this is the one who took the picture of the Vikram on the moon, which is a very classical picture.
That's right.
So these cameras to function and bring the image back to Earth, it has to communicate to Vikram and then it has to communicate back to Earth. So that channel should be open.
Tell us the hops that it takes during communications. How does the command go from here and how long does it take?
There is a series of commands. It's not just one command, you now come out. No, it's not like that. There are series of commands which need to be uplinked. And what we do is we uplink all of them. Then most of the commands are timed, that you do it execute only at this certain timing. So there is a clock running inside. There is a reference to that clock. So we send all the commands up there. Then it registers inside the computer memory. Then we read back all the commands that and then check it again whether it is received and stored in the appropriate location correctly. And this verification goes. And after all this verification is done, then you leave it to execute. So it will be executed at the time which we have planned a priori. So while it is actually getting executed, we don't do a real-time commanding. If you want to really do a real-time commanding, that's also possible.
How much time does it take for a real-time command to be received
See,
and
the
executed?
signals travels at the speed of the light. So the moon and back, it takes few seconds, 1 or 2 seconds at best.
And
Not even that much, it's actually much lesser. So it can be reasonably real-time, but then real-time commanding is not a preferred option in most of these cases, except, say, if you want to get, if it is moving, it has seen a obstruction, want to do something, or some of the attitude orientation. So camera or antenna need to turn and look at the ground station a little bit. So we want to little move and then see whether it responds.
so that is the real-time command being given.
Such thing we can do in a real-time.
And if you want to orient the camera in another direction,
Yeah.
and you give a command, how long does it take?
It will do in a matter of
seconds.
1 or 2 seconds.
And you see the response
immediately we see the response.
What is the speed at which you get this
There
data?
is a difficulty there. See, if it is an orbiter like the Chandrayaan 2 orbital where there is a high resolution camera, we have a certain transmission rate which is decided by the band in which you are using. This time we are using X band, sometimes we use S band and different bands for communication. The throughput data rate is decided by the band, the signal power, the antenna in the ground, the visibility, etc.
Correct.
So through that decides the rate at which the data can be transmitted. And it also needs to have power. For example, if you want to take a picture taken by Pragyan to be sent to rover and rover to ground, it takes actually hours for sending one picture. Reason is simple, because the power available on board of this Pragyan is very low. The battery capacity is very less, because the amount of power generated is just from this panel.
Correct.
And the sun is not illuminated very bright on it. It's almost at the fag end of its life. So we keep the power very low. So typically a picture takes very long time from Pragyan to reach. But if it is a camera on the Vikram, it could be faster. But if it is from an orbiter which has a higher gain antenna, then it could be still faster.
Still faster.
It's all limited by the onboard power.
What are the next things we have in mind for Aditya now?
So Aditya, after its earthbound maneuvers, which was going higher and higher to almost 1.25 lakh kilometer, now it has now left Earth from the highly elliptical orbit.
Day 4 yesterday, no?
Day 4, yesterday. So it started its journey towards the Lagrangian point, L1. It will take almost 110 days for travel from here to reach there. So right now nothing more need to be done. Now the final burn of the earthbound burn is now completed. It acquired the required velocity, and with that velocity it will simply go straight to the targeted point L1. But the L1 is also moving, Earth is also moving, Sun is also moving. So it's a combination of movements, and we hope that mathematically it matches exactly at L1. And this will continuously be monitored, because we call it orbit determination. So its path is continuously being measured using ground stations that we have. We have a deep space network, antennas are there. So it will measure the arc through which it moves, and we will make a prediction, mathematical prediction. It's actually moving precisely there. And it's moving such a far distance, 1.5 million kilometers.
Yeah.
So a small error here can make a thousands of lakhs of kilometer error there.
Yeah.
So we need to very precisely
yeah.
and there are opportunities for correction between us.
Interesting. Tell me, where are all these things fabricated?
It's fabricated at Bangalore at the URAO Satellite Center. Here itself, where we stand, this is the place where we build all the satellites. So most of the hardware from this came. Though the whole integration takes place here, but it has sources of these components come from various parts of the country in various ISRO centers. See, I can tell you, it has propulsion, for example. It has engines. You would like to go and see closer?
Sure. Yeah.
You can see the engine there. See, this is the landing engine.
That's right.
There are 4 such engines, and there are control engines. These are fired to make it orientation change. So this engine plus its own feed system, the propellant tanks, it comes from LPSC Bangalore.
Okay.
And manufactured at Trivandrum, partly manufactured. The engines are manufactured at Trivandrum. Then tanks and propulsion elements are manufactured in Bangalore, and they come and assemble here. The cameras on this came from Space Application Center, Ahmedabad. So there are many cameras. There are cameras here, there are cameras in front, and when the rover came out, there are cameras which picked those images. There are cameras which will measure the speed, velocity, etc. So they are built at Space Application.
How many cameras are there?
There are cameras just for observation. There are cameras for measurement. For example, we have a camera which measures the horizontal and vertical velocities of this movement. There are camera meant for looking at the hazard avoidance cameras are there, optical cameras.
Which you used.
Yes, for the last minute vertical landing. So it's about 8 cameras, I believe.
So where exactly you said then when these things are made here, and how many such payloads can you fabricate simultaneously at this place?
Here we have clean rooms and assembly facilities. We have test facilities. The total number of such assemblies possible is limited by the space and test facilities, checkout, etc. So I know that there is a record, even up to 10 such assemblies can be done at a given point in time here.
This kind of a payload, for example,
Yeah.
Vikram lander, how much time does it take from start?
See, if you start from the conceptual stage to realization, it's not a small short duration. It's a very long period of time. It could be as much as 6 to 7 years. But building instruments are the most complex part of it, and it goes through so many tests, and every test will make a change in the design. So we have concept of models. We will first make an engineering model, which is more resembling to the actual thing. Then that will go through testing, and that will reveal certain deficiencies. After engineering model is qualified, we make a proto generally. Then after proto is, it will subject to the flight-like environmental testing, then the flight model is prepared. This is a standard procedure. But if it's a proven satellite, for example, a communication satellites, we don't have to do engineering model, we don't have to do proto model, we make straight away the flight model.
If you had to make a new communication satellite, in 1 year you can actually fabricate
Yes, if all items are ready with us, it's 1 year of assembly testing.
What percentage of the components are indigenous?
In spacecraft, if you look at spacecraft is more and more of electronics driven. It's not a mechanical or other systems. Other than high-end processors, chips, memories, and some specific radiation hardened devices, everything is Indian. But in terms of the money, if you look at those elements are very costly. If you look at the whole of this hardware, what you see outside is all Indian. But there are some still elements which is inside, which is the highly integrated circuits, memories, FPGAs, which you have no other options for, even detectors. We take years to get it. We have been progressively indigenizing them. So in terms of cost, I will say it is typically 40% to 50% of the actual expenditure of building it goes into those very small items. Whereas this number is almost 90% for indigenization content is almost 90% for rockets, whereas still it is 60% for satellites.
How does the quality compare with what you used to import?
See, there is always a quality control processes. We have been indigenizing so many things in the past. For example, if you look at materials, most of the materials you use here are all Indian origin from Indian companies, and they are on par with the world. For example, I'll tell you, electrical cable which are used for wiring, they used to be imported. All spacecraft cables were used to. So today we don't import anything. It's actually made in India. 3 companies in India are making it, and we worked with them to convert those.
And these are these private sector
companies,
supplies which you have.
Yes.
Other than cables and all, what are the other high-end stuff which private sector is contributing to your space program right now?
So many are there. For example, in terms of devices, packaged devices like gallium arsenide devices, memories, passive components, electronics, capacitors, resistors, PC cards.
They are being made.
They are all being made here. When you go in the higher end, then you will see sensors, optical sensors, all mirrors, all lenses, all optical assemblies are made here. The solar cell, what you see here, the solar panel is indigenous, but the cell here is imported. Cell is still not made in India.
What kind of power does it generate with this solar panel once it gets the full sunlight?
See, here it depends on the orientation. It has 3 sides solar panels are there, but sunlight will fall only on this face in the nominal location. So it generates almost 1.4 kilowatt of power.
And how much fuel do you still have remaining in your?
Our estimate is that after the landing process, hope process, etc., around 90 kilogram of fuel is left, which could be enough to do some more interesting maneuvers.
So those maneuvers are actually going to happen.
Let's hope. But there are many challenges. I must admit that. See, what happens is when the temperature goes below 180 degrees,
you don't know how the
liquids will not remain liquid. It will become solid. And every pipeline will become solidified. Every tank, every component.
You don't know what has happened.
And it has to melt back to the liquid. And with all our confidence, we will do something. Understand?
Something different from this. When you're looking at the countdown for a launch, it says T minus whatever. Suddenly you get something and the computer says you have to stop. How does it happen?
See, in every launch, there are almost 2,000 measurements. And these trends can be understood by a doctor like you looking at your heartbeat, no? You go to ECG.
Yeah.
So once you look at those curves or the graphs, you are able to understand what is a pattern, and if there is a kink in the pattern, if it's not moving in the right direction, there are expected bounds. So there are 2 ways of finding out. One is through the heuristic way of finding out. Through my expertise, I can find out. Second method is you can train a computer to do it.
Correct.
So we train a computer algorithm we call the automatic launch sequence, and that will check all the parameters. And when some parameters are out of bound, then it will immediately check some other thing to verify whether this out of bound is right or it's a fictitious. Something can go wrong with the sensor. So to validate, there are other checks. So we call it triple modular redundancy, which will decide whether something need to be stopped or not be stopped.
Now coming down to Gaganyaan, for example, where exactly are we?
So Gaganyaan is a very complex project, though it's like launching something, but launching up there is very easy, but bringing back is very, very risky. And even for launching, we need to be very sure that nothing can go wrong because human beings are involved. We have given a very optimistic schedule when we started the Gaganyaan of doing it in 4 years of time. We faced many challenges. So we had to do many re-engineering, redesigns to overcome that challenges. But the biggest challenge to me is the safety of the crew.
Correct.
Suppose you look at Gaganyaan, if it happens, the first mission ends up with some problem, recovery will be very difficult. Right. It could be 5 years, it could be 10 years. So I talked to my
human beings involved. No?
Yeah,
So
I talked to my teammates and also talked to government also as well, and mentioned to them saying that it is very risky to go a fast track approach in this. It has to be a very cautious approach with the full confidence on the very first mission. So we thought that we should add additional tests, additional validations, additional measures to ensure the first time when we do it should be right. It is of course discussed with the government. It is also going to be discussed with the Space Commission and many other fora. And we would like to set the clock slow for it.
Some idea about?
Yeah, what we are trying to do is there are many tests, hundreds of tests happening now. And we would like to make sure that in the next 1 year, most of those tests do happen. And manned mission, of course, the final manned mission cannot happen before 2025. Yeah. And the biggest test which is going to happen, the crew aboard test, is going to happen next month.
You say 26th?
Yes, 26th
of October.
Yeah.
So, we have always used the phrase rocket science. For the first time, we are getting used to or understanding what it exactly means. Why is it that we took 40 plus days to get there, whereas the Russians, even though it was a failed mission, made it there in just about 5 days?
No, it has to do with quite a lot with the rocket which they used. The rocket we used is the LVM-3 rocket, which has a capability of 4 tons to GTO, and the corresponding payload capability for putting the satellite in an orbit, which will directly take it to moon, needs little more power. Typically, if it was around 6 tons to GTO, possibly we could have done that. The Soyuz rocket, which took the Luna 25, had that type of capability because their upper stage is very powerful upper stage, which actually did the final boosting to put it in the translunar tract right away. So they could travel in 5 days of time. So when the rocket is not powerful, what you have to do is you have to make the satellite more powerful. It should have a propulsion which should be able to do that translunar injection. But that also cannot be done in one go. So that's why we have to do a maneuver which is moving around the Earth in multiple passes and do the energy addition or the velocity addition at the most efficient manner. You know that every movement around the Earth is in an elliptical orbit. When it is closest to Earth, we call it perigee, the closest point. Apogee is the farthest point. In the perigee is the highest velocity zone, and if you can impart the energy to it at the closest point instantaneously, that is the most efficient. But we cannot do that. We have to do it over a period of time. So ultimately what happens is the propellant that you are consuming to do the energy increase is minimized. So it is done in multiple phases to raise the orbit, so that the last orbit firing will raise it to such a level that the final orbit will encircle the moon. So that's how it took more time in around Earth. Then second is around moon also we took more time. That's why the Chandrayaan 3 craft has 2 parts. One is the propulsion module, which you can see here. From this point to this point is a hardware just to take the lander to moon. Typically satellite engines are more efficient, and once the rocket part goes away, the mass comes down, so you can make it do more efficiently. So this is a new way of doing it, and we had done right from the Chandrayaan 1 time onwards. We did it for Chandrayaan 2, we did for Mangalyaan, and we did it for Chandrayaan 3 as well.
So what happens to this after it then disintegrates?
It doesn't disintegrate. It actually goes to an orbit of 100 by 100 kilometer around moon. It is still there, it is working. But we made this time that this is not a functional element today. But we have one payload on it, which is called SHAPE payload today, which is going to do an observation of Earth.
And what kind of measurements does it do from there?
It is actually looking at Earth in a spectral nature of the Earth is measured, and it is trying to find out the similarity between Earth and a future exosolar planet that is a planet which around any other star, not moon, sun, if you ever discover, if you are able to get the spectral characteristic of the emissions coming from that object and the emission coming from Earth, if you can find certain comparison, you can say the life controlling emissions which is of various nature, presence of water, presence of oxygen, presence of bio systems, etc. So if you can characterize the Earth in a spectral manner, then you can characterize that object's emissions through the atmosphere of that also in the similar manner.
Anything which Pragyan or Vikram have sent so far about the moon surface which we have not disclosed to the world as yet?
Yeah, there are interesting things. For example, the moon's topography, the surface characteristics. We did two important measurements. There is a payload called Chaste, which we pierced a probe into it, which is a composite material. Inside there are heaters, which apply some heat temperature and measure the temperatures. And also look at how the surface is like a very thick, very good insulator. So we found that even though the upper surface is room temperature, little higher temperature, within 10 centimeter down, the temperature has gone so much less. So that means the heat transfer into it is through very, very less. This is a new finding. Similarly, the rover, when it actually moved on the surface, the wheel, and also the landing process, we were expecting a lot of dust. Nothing was seen of that type. We found a very mild dust coming out, not huge dust. But that was surprising. And finally, what we found is the surface is not very dusty. It's actually chunks of the soil is coming out. It's not very, very dusty or powdery, which is a very important finding. Why it is it's not so in that zone? Because whatever data that we have collected from various other sources for people who have already gone to moon, collected the samples, especially in the equatorial region, we are speaking about dust as a major issue.
Correct.
And we didn't find it to be a major issue in this zone. So definitely it's an interesting finding, and it needs further investigation. What makes it to be like that, and what are the materials that make it to be like this? It's definitely not water, of course.
Sure.
Okay.
We are in the Assembly, Integration and Testing Clean Room Facility 2. Tell us, what exactly do we see here?
See, that's a satellite which we have just now completed the integration, testing and ready for launch. It's called XPOSat, X-ray polarimetric satellite, to study basically black holes.
Okay.
And basically what happens is when black holes eat into other objects like the stars, suppose another star comes closer to black hole, there will be a material attrition which will be drawn because of the huge gravity in the black hole. The material will start flowing like a tunnel into it. It will generate so much of radiation in the X-ray domain. And this radiation, if you are able to do the polarimetric measurement of it, you will be able to get an idea about the...
I see. And what are all these things here which we can see right now?
Each of this is a station where one satellite can be assembled.
Okay.
So this is a test fixture which you can move in different directions, tilt it up, orient it. When you want to assemble, no, it's a station where, like automobile assembly station, you will see.
Correct.
It's similar to that. So you can see one of the structures there. IDRSS is an Indian data relay station, a satellite, which is supposed to be built under part of the Gaganyaan program.
I see.
When the crew module is in orbit, they have to maintain communication between Earth and crew continuously. But we don't have ground stations all across the world. So what we do is the crew will communicate to the satellite will communicate back to us.
I see.
So this will remain in geostationary orbit. So we have to build 2 such satellites and launch prior to the Gaganyaan program. So
interesting.
yeah.
Okay.
So
When you talk about satellites and communication, there's a lot of talk about NAVIC.
see, first of all, you have to understand the NAVIC is created for a different purpose. It was created for a strategic purpose.
Correct.
And it was created when there was a denial of GPS to us.
I remember, yeah.
So then the primary objective is to provide services to the strategic forces. So typical GPS gives you an accuracy about 20 meters. Could be better also. But we have designed NAVIC for an accuracy of all 3 meters, because it is based on the stationary set of satellites, not a moving set of satellites. And it is actually demonstrated. But unfortunately what happened is, after our launching, the penetration of that into our defense forces has not been very strong. So I have taken it up much more seriously, and the present CDS also is very keen to make sure that it actually happens. We had a series of meetings to make sure that it gets into the Army, the Navy, the Air Force and all their equipments. The equipments which are inside are mostly GPS based equipments, and to convert from GPS to NAVIC requires a lot of work in terms of hardware development, change over a period of time. But they are on the job. I believe in another few years that transition from GPS to NAVIC will happen.
I see.
Second,
Looking forward to it.
second point is that, of course, when you have a capability, it has also a civilian signal. Now, the civilian signal should be used by civilian people, and we have given a lot of thrust to that in the last past. But the civilian utility was affected because of various important reasons called the frequencies. So, you know, GPS is operating in a band called L1 band and L2 band, whereas we were denied those bands by GPS long back. So, we built the NAVIC around two other bands called S band and L5 band. So, these two bands are not there in your mobile chips or chipsets.
Happening now, though.
So, we said that for anybody to use this in mobiles, they need to have an additional chipset in L5 and S band, which is creating problem for them to additional cost, additional infrastructure, etc. is required, antenna required. So, we decided that we have to add L1 band and L2 band into NAVIC. So, we built it and launched satellites in L1 and L2